So today we're going to be talking about glycogenolysis. So this is the process where glycogen is released in glucose form in order to increase blood glucose levels during the fasting state. So specifically I'm going to be talking about the amplification cascade, and all of the reactions I'm going to be explaining are occurring in the cytosol. So first we have glucagon, which is our hormone, and it's being released from the alpha cells of the pancreas. So glucagon is going to bind to our hormone receptor. Then our hormone receptor is going to basically signal to our G protein, which is made of 3 different subunits. So we have our alpha, beta, and our gamma subunits. So the G protein currently has a GDP, but it's going to bind to our hormone receptor. So we're going to have our beta is now here, alpha is there, and our gamma is there. But when this happens, the hormone receptor is going to basically replace our GDP. Now it has a GTP. So when this happens, our alpha subunit is now going to leave the other 2 subunits and travel over to adenylyl cyclase. So our alpha is going to bind, and it has a GTP. So our adenylyl cyclase is going to produce cyclic AMP, or I like to say CAMP. So we're going to use this reaction. So ATP, and GTP are kind of interchangeable, as we learned previously in the course. So our ATP will now be converted into cyclic AMP plus PPI, which is our phosphate groups. So our adenylyl cyclase is going to produce an insane amount of cyclic AMPs. So times basically a lot, so however much we need. And then we will have a GTPase, which will remove this phosphate, making it back into a GDP, and then our alpha subunit is going to go back. Basically, these are going to go back into place, meet in the middle, and this reaction is going to stop. So the step 1 is complete. And if you make too much cyclic AMP, then we have a cyclic AMP phosphodiesterase, which will actually break down our CAMP into AMP. So once we have all of the cyclic AMP, where is it going to go? So it's going to go to our protein kinase. Protein kinase. So 4 CAMPs are going to bind to this protein kinase. So see, it has 4 sites. So it has 2 regulatory sites and 2 catalytic sites. So 1 cyclic AMP for each is going to bind. And now we will have our 2 regulatory sites. R and R are still bound together, but our catalytic sites are now free to covalently modify our next enzyme, which is phosphorylase kinase. So let's just keep in mind this reaction. So cyclic AMP plus H2O will give us AMP. Okay, so on to our next step of the amplification cascade. So we will use this AMP basically to reset our reaction of phosphorylase. So phosphorylase has phosphorylase B, which is the inactive, and the phosphorylase A, which is the active state. And as you can see, phosphorylase B is a dimer because it has 2 different subunits. You need to keep that in mind for this reaction. So phosphorylase B can be covalently modified using 2 ATPs so that we can add 2 phosphates onto this little dude. So we'll add our phosphates, and then it will give us our active form, which is phosphorylase A. And we needed to use 2 ATPs, so we could do 2 of these phosphates, and then we're left with 2 ADP, and then our phosphorylase A will be in the active form, plus having those phosphates on there. And then phosphorylase A is actually going to be the enzyme that goes into the reaction. Oops, I can't move that. That tells glycogen to be released as glucose. And that's a whole other reaction that I'm not really going to talk about right now because it takes too much time. But with phosphorylase A, we're obviously going to need controls. So what are our controls going to be? So we have a phosphatase. Let me write that down. Phosphatase 1. So phosphatase 1 can bind to phosphorylase A and inactivate it. So when this happens, the phosphatase 1, let's just circle that, will bind here So then it makes this now inactive complex. But the problem is that phosphorylase A actually exists 10 times more than the amount of phosphatase. So that means that if all the phosphatase ones are bound to the phosphorylase A, then there will still be 90% of the phosphorylase A being active and still carrying on this reaction. So we're going to need a second control to actually put this to a stop. So when the blood glucose levels are high, we want to turn off glycogenolysis, because glycogenolysis is the reaction that increases our blood glucose levels. So if they're already high, there's no need for this reaction. So with increased glucose levels, glucose can actually bind to phosphorylase A, and then it will basically remove the phosphates and turn it back into phosphorylase B, which inhibits the reaction. So in order to control this, glucose levels, either if they're low, it's going to release glucagon so that this reaction continues or starts, or if glucose levels are high, it will inhibit the reaction, and then you won't have any glycogen released as glucose.